All right, sometimes we're going to describe light using waves. Other times we're going to think about light as being comprised of particles, and a particle of light is called a photon. And there's an energy that's associated with each particular photon, and that can be calculated through this equation. E, which is energy, is equal to Planck's constant, which is symbolized with H, times the frequency of the photon, which is symbolized with the Greek letter nu. The value of Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. This can be thought of as the amount of energy that is associated with a photon for every hertz of frequency that that particular photon has. So you can see that's a really small number, and that actually makes sense because if we remember that the frequency of photons is extremely high, of course, we're going to need to multiply that by a very small number to get reasonable values. Now, if we remember that the speed of any wave, a light wave, of course, speed is 3 times 10 to the 8 meters per second. But if we remember that the speed of any wave is equal to the frequency times the wavelength of that wave, of course, if we divide both sides of this by the wavelength, then we get the equation speed of light over the wavelength of light. That's going to be equal to the frequency. And if I take this portion of this equation and I substitute it back into my original equation for the energy of a photon, so we're going to plug in C over lambda for the frequency, we get another equation that allows us to relate the energy of a photon with its wavelength. So that's going to be energy is hc over lambda. And these two equations here and here allow us to see that the energy of a photon is directly related to the frequency. So light particles that have a higher frequency or that are oscillating back and forth more quickly, those are going to have higher energies. On the other hand, because on this side we're dividing by the wavelength to get the energy, we see that the higher the wavelength, the lower the energy. So this means long wavelength waves have low energy, whereas short wavelength waves have high energy. Okay, let's look at this with a bunch of different types of light waves. All the different types of light waves, we sometimes call this the electromagnetic spectrum. And the various types of light waves that are in the electromagnetic spectrum, they range from radio waves to microwaves to infrared light. Visible light, this is the light that we can see. These are types of light that we cannot see. Then we have ultraviolet light, X-rays, and gamma rays. These types of light here and these types of light here are types of light that we cannot see. Of course, we only see visible light. And if we look at these various types of light, we can estimate the wavelength of each type of light and also the frequency of each of these types of light. And it turns out that radio waves run from about, 1 to 1,000 meters, somewhere in there. Microwaves are usually around 0.01 meters. Infrared light is 10 to the negative 5th or so meters. These are all estimates based on powers of 10. Visible light is 10 to the negative 6 to 10 to the negative 7 meters. You can see as we're going this way through the spectrum, the wavelength is going down. UV light, 10 to the negative 8 meter. X-rays, 10 to the negative 10 meter. And gamma rays, 10 to the negative 12th meter. And just to give you an idea of the size difference as we move from one spot to the other, this is on the order of the size of buildings or people. This is like a small ant. This would be roughly the size of a pinpoint. In the visible region, these sizes are on the order of the size of cells. We get around here, we're looking on the order of molecules. X-rays, the wavelength of X-rays are about the size of atoms, and the wavelength of gamma rays are about the size of the nucleus in an atom. So we're going all the way from people to the nucleus. Huge changes, huge factor of 10 difference as you move across the electromagnetic spectrum. In terms of the frequency of these particular different types of light, radio waves vibrate about 100,000 times a second. Microwaves vibrate about 10 billion times a second. Infrared, that's going to vibrate about 10 trillion times a second. And then how fast these light waves vibrate just increases incredibly. Visible light's 10 to the 14th. These are all in units of hertz, by the way. So these are vibrations per second. Ultraviolet light about 10 to the 16th hertz. X-rays 10 to the 18th hertz. And gamma rays 10 to the 20th hertz. And if we remind ourselves of our original equation, remember our original equation, we see that energy scales as frequency, but as the inverse of wavelength. So energy of a photon is going to become greater as we go to higher frequencies. We see that energy is going to increase as we go this way on the electromagnetic spectrum. This is pretty important because the damage a photon can do to various materials is going to depend on the energy that each particular photon packs. And this is why you'll often see people concerned about X-rays. I mean, you don't want to get a whole lot of X-ray. You don't want to get an X-ray every single day. You know, 1 or 2 or 3 a year isn't going to be a problem. But you don't get X-rays every single day, because when you have X-rays shined onto you, that's some pretty high energy photons that your body's having to deal with. We know that we go out in the sun, we're exposed to ultraviolet light, and that ultraviolet light can, the photons from that ultraviolet light that can mess with the molecules in your body, actually the DNA in your body, and then cause cancer. That's why we wear sunscreen, to absorb the ultraviolet light. On this end of the spectrum, we see photons that do not have high energy. Infrared light, microwaves, radio waves, you needn't concern yourself being exposed to these at all. I mean, for example, your eyes are exposed to visible light all the time, and that doesn't cause much damage to your eyes, if at all. So again, we see that energy increases with frequency, but notice that it decreases with increasing wavelength. As the wavelength gets shorter, the energy goes up.